For this week's individual assignment, we're looking at acceleration measurements and integrating those through to get position and finding out something about the uncertainty along the way. And in the lab, we measured some acceleration with an accelerometer, a single component, and we integrated it to get velocity and position. And we saw that that position especially drifted off really quickly. So we're going to try to investigate that in this Jupyter notebook and get a little bit more detail about what's going on. So first we'll start by importing all the usual stuff, and I'll run that cell. And we've got some calculation functions. These are things that we had from last week's assignment. We had a moving average calculation and a smoothing calculation that we pulled from some previous work, and we generated this derivative function in order to be able to take first derivatives. So we'll keep those so we can use them again. Now, in the lab, we measured an acceleration, and we don't actually know exactly what the underlying acceleration was for the motion we made. We only know what we got from the measurement. So if we want to understand what's going on, we'll need to simulate a real acceleration so that we've got something to compare to. So we're going to create our gold standard for acceleration by starting off with a position value and then taking the derivative of that position to get velocity and the derivative of that velocity to get acceleration. And we know from last week that our derivative function, this one up here, works pretty well for doing that as long as the signals are really clean and smooth and don't have noise on them. So let's try that out. I'm going to define this function int plot here to just plot out some data so that we'll have that around whenever we need it. I'm going to use 10,000 points for my time space. I'm going to go from 0 up to 5 seconds over those 10,000 points. And I'm going to set position equal to this function. So it's using this norm PDF, this Gaussian distribution with a sinusoid inside it to produce a wave that's in a Gaussian envelope. And that's a function that I just pulled out of the air, knowing that I wanted it to be something like that shape. And it results in a position like we've got here in green. So it starts off not moving. It starts moving up and down, it moves further up and down faster, and then it tapers off again. So that looks something like the data that we think we had in the lab. We were sitting still, we moved it, and then we were sitting still again. And I've plotted it out here, magnified by 100, just so that we can see them all on the same scale. The velocity we get in orange. The velocity is just the derivative of the position, like we got last week. And the acceleration, just the derivative of the velocity. So we've got this plot coming out. And I'll run this just to make sure that we do still see the same plot coming out. So that's good. That's believable motion data. The derivatives all look like they behave themselves. And everything does come back to 0 when we're done. So that's good. So now let's test our integration. If we start with the acceleration, we should be able to integrate back to get the velocity and integrate back to that from that to get the position. So our target in question 1, create a new function called integrate that does the same sort of thing as the derivative function, except this time we're going to be integrating a time series. And this is the same kind of calculation that we did in the lab. We're just adding each step we go along, we're adding to the integral. So we'll start with the acceleration data and work our way backwards. And I'm going to define this function integrate. There's my time base. There's the X time series that I'm integrating. And I'm going to return a new time series that's the same size. Sorry, an integration series that's the same size. And it's going to be 0 to start off with, and we're going to add to it step by step for the integration. So I'm going to go for element 1. So element 0 is going to be 0. Element 1 is going to be a little bigger. Element 2 bigger still, and so on, all the way up to the end of the time series. And you're going to have to add some code here. You won't see this code in your version of the assignment, but I'll explain what's going on here. If I take xi and xi minus 1 and divide them by 2, that gives me an average value over the short time period between ti minus 1 and ti. So that's the average value that x was. If I take that average value and multiply it by delta t, that's the increment that I'm going to get in the integration as I go from time t at I minus 1 to time t. And so finally, the integral value that I'm going to have at time t of I is equal to the integral value that I had at time t of I minus 1 plus whatever the incremental value was. So this is doing exactly the same kind of thing that we were doing in the lab. And I'm going to test it now to see if, starting from the acceleration, I can integrate backwards to get the velocity and the position. So let's run it. And I ran that int ac function down here. I assigned the values returned from it to P1, V1, and A1. And I called my plot function, the one that I defined up here, to plot them all out. And sure enough, it looks like I got back the same stuff that I had before. Those two graphs look pretty close to identical, so I'm feeling pretty confident about my integration now. So now that I know my integration is working, let's get the lab data and see what happens. So I'm going to import my lab data. And this is my data. It's in a file called rawdata.csv. And if I import that, I can print out some values. And the ones I'm interested in are this second column of A1 values. This is a time, apparently in microseconds. So I'm going to make traw equal to a small segment of the input, the region that I'm interested in, which runs from about 41 seconds up to about 47 seconds. And I'm going to divide it by 1,000,000 to make sure it's in seconds. The acceleration data that I'm bringing in, I'm going to take the same corresponding values from column 2, that's these ones. And then I'm going to use the calibration relationship that I got in the lab to turn those into accelerations in meters per second squared. So this is the raw input data that I got from my analog read values, and it's divided by 10. This is what it looked like when I converted it into an acceleration. And these little glitches here, I think those are actually real acceleration data. But I've also got a bunch of noise on here, and I'm not sure just how much. If that was just no noise, there would just be a single straight line there rather than little oscillation up and down. So now I'm going to run my calculation on my lab data. And I run the calculation on my lab data, and I wind up with the kinds of results that I saw in the lab. That is that the velocity was following along reasonably, but drifted off a little bit. And the position, it still shows these oscillations, but it's got an even stronger drift in it. Now, I'd like to know where that data is coming from for the drift. So I'm not surprised at these results. That really confirms what I saw in the lab. I've been able to duplicate the same thing by integrating the same acceleration data. So I don't think I had an error in my calculations in the lab that made this happen. So let's think about our acceleration data. Well, it's going to have both bias and noise uncertainty. When we set up our accelerometer and calibrated it, we didn't get our calibration perfect. So when we read the value from our accelerometer, even if it's not moving, it's not going to give us exactly 0. It's going to give us something that on average is biased in one direction or another. Likewise, every time we make a reading, we're going to get some noise. So as a result, we can have our underlying acceleration, which might be this stuff that we measured up here, this blue line, but it's going to be corrupted in our actual data recovery by the fact that it's going to have a bit of an offset from 0 and also some noise in the data. And down here we can illustrate that. We've got this red line is the actual acceleration value from our ground truth, and it's a nice smooth line with some oscillation to it. Now if we had a random bias, this orange line shows what that would look like. It'd all be pushed up just a little bit above 0. So if the acceleration is biased in a positive direction, then the velocity is going to be constantly increasing in a positive direction, and the position is going to be exponentially increasing in a positive direction. So that bias is going to cause some difficulties. In addition, we might have some noise. If we had noise on our signal, it might look like this blue stuff that's in behind. Now, these are all exaggerated just so you can see the differences. But let's look at what happens when we have some noisy data. Down here, I'm going to run the calculation on the data that just had noise in it, no bias. And I'll plot out the results. And because I know what the underlying position should be, that's P, then I can take what I got, P1, and subtract P, and that'll tell me what the actual position error was when I ran this calculation on my, my ground truth gold standard data. So I've taken all of this and I've plotted it out. There's my noisy acceleration, but the noise is random, so it oscillates above and below 0. And we can see that the velocity, well, in here it should be flat, but it's actually got some variations in it coming about due to the noise. It still follows up and down and makes sense compared to the acceleration, even with the noise. But when we get to the end here, it's above 0. And likewise, the position has drifted off in one direction because the effects of the noise are driving the drift off in one direction, but it could just as easily be the other direction. Let's try running it again. And running it again. And running it again. Of course we don't get any difference because we didn't change the noise value. But let's go up here and rerun our noise and get a new random set of noise. New random set of noise, it still looks a lot the same. But if we come down here, this time we've got the position error drifting off this way. New random set of noise, and we run it again. Now it's drifting upwards, but not as badly as it was before. New set of noise, and run it again. And this time it's running off with quite a large effect. So we're getting a random effect due to this random noise that's leading to drift, even if the noise is only a oscillating effect around 0 with no bias. So even noisy data is going to cause us problems with this drift. Now let's look and see what the situation is if we have a consistent bias. We expect that our consistent bias is going to drive it off consistently in one direction or the other. So here we saw the noise, it was going up and then it slowed down a little bit, and it's got not really a consistent trend here. But if the bias is consistent, in this case a consistent negative bias, It's consistently moving the velocity down just a little bit below zero. And the result is the position consistently goes increasingly below zero. And we've got a position error that's increasing with time. Now, you're going to do this calculation yourself. There's no code in here, but this is the kind of thing that you expect to get out. And in fact, you could have it increasing consistently up that way or more sharply down this way. It'll depend on what random values for your bias uncertainty are generated each time. So in reality, we're going to have a combination of both the noise and the bias. So let's consider some random combinations of bias and noise. And let's do 20 of them. So if we repeat this calculation here 20 times and get this red line 20 times and plot it out 20 times, then we'll see that it veers off in multiple different directions. But overall, it seems to be going off by somewhere between 10 and 15 in either direction by the time we get out to 5 seconds. So the uncertainty by the time we get out to 5 seconds is about 10 to 15, and because this is position times 100, that's about 10 to 15 centimeters. So that's a fairly large uncertainty on our scale of measurement. Now, we'd like to be able to quantify this a little better than just providing a picture. And so we're going to try to estimate that uncertainty a little better. We can't do it analytically. At least I don't know how I would tackle this analytically to try to predict this, because there's a whole lot of stuff going on there. It's the collection of a whole lot of different noise factors plus the bias. But we can do it really easily with a Monte Carlo simulation. Up here, we've run it 20 times. So we've got 20 different values for what our position error might have been after 5 seconds. If we run it 100 times, we can plot a histogram of those position errors. If we run it 1,000 times, we can plot a histogram, and we can compare it to a Gaussian distribution. And sure enough, if we plot a histogram, it compares really closely to a Gaussian distribution if we run this calculation 1,000 times. And that's going to take quite a long time. And having run this calculation 1,000 times, we can get a mean which is really close to zero, and that's encouraging because we expect our uncertainty to be evenly distributed around the correct value. And we wind up with a standard deviation of about 0.064 or 0.065. So standard deviation of 0.065 meters, that's about 6.5 centimeters. If we double that to get a 95% uncertainty, that would be about 13 centimeters. And that matches up here with what we saw in terms of the spread of these lines and how they varied. So after 5 seconds, with the signal that we put in, that's this acceleration in blue here, we expect our uncertainty to be about plus or minus 13 centimeters for the position. Next question, does that magnitude of uncertainty depend upon the actual acceleration? Or is it going to be relatively independent of the acceleration? So if I try doing the same calculation, but with the acceleration nominally equal to zero, just plus a little bit of bias and noise, so as if I was holding the device still on the desk, I get exactly the same kind of behavior for the position error. I'm still getting about 6.5 centimeters standard deviation, or about 13 centimeters, 95% uncertainty value. So I can say that it's always going to give me, from this calculation, it looks like it's always going to give me something around plus or minus 13 centimeters position accuracy after about 5 seconds. Now, depends on whether you're thinking that's really good or really bad. It will depend on the application. So what I'd like you to do is, in this assignment, I'd like you to go through and fill in these pieces of code that I've blanked out here to get data that looks like this, and see if you can replicate these kinds of results. And if you can do that, then you'll have mastered the ability to run a Monte Carlo simulation on a complicated measurement situation to make a reasonable estimate of uncertainty. So good luck with your assignment. I look forward to seeing some good results.